So also from my side, welcome to this 8th and last seminar in this series. We're really excited to have had the chance to have this seminar series, and I guess all of us learned so much by all the experiences. Today, it's already the final one, final session. We have a packed program, so we should kind of therefore kind of immediately get started. So this is just as a reminder here, the 8 weeks that we had from starting from best practices, now coming to the using citizen science to inform hydrological models. To start this, the first talk will be by Professor Lutz Breuer from the Justus Liebig University in Gießen in Germany. So we appreciate that you spent your evening with us here presenting. Lutz has background from physical geography and has been for almost 10 years now a professor in hydrology in Gießen, working on a lot of different things, mainly with focus on chemical processes in catchments, places around in Germany, but also around the globe at many different places. And for a couple of years, he has developed an interest in citizen science, which is a way to kind of include the public and the society, both to inform the public, but also to include them in the research. And several interesting studies came out of that work. And we're very happy to have you with us, Lutz, here. And I give the word to you.
Okay. Well, thanks for the invitation, and it was really a pleasure to have this seminar series. We will take a second and then the presentation should start. Does it happen?
In the presenter mode?
No. Okay. So
yeah.
I'm going to talk about the opportunities of using citizen science data in hydrological models and give a final, well, estimation or suggestion on where the limitations of these approaches are. The background of the study that I'm presenting is a work that we're doing in Kenya at the moment, which has started a couple of years ago. And the reason for that is that, as in many other countries, the data that the people or the decision makers are needing for water use, for domestic consumption, or for flood forecasting, or climate change impact analysis, as well as for agricultural purposes such as irrigation or the crop water requirement. For all of these things, you need data that you finally need to feed into models to be able to make projections or to run scenarios, to develop ideas for management. And that's why we think that the collection of citizen science data is one thing that has its benefit, but the other option and the other benefit that we see is that they should be and could be used for model applications. Because the parties that are interested in these countries are the planners, the consultants, the extension services for the farmers, but also the public institutions or the politicians and the scientists. And of course, there are, depending on the country where you go to, other questions like rivers for transport that need water. Big issue in Germany in the past summers, which have been very dry and the large rivers were not able to be shipped. So the model applications is one thing, but the projections for these people who are interested in the data and the results is another option. The study I'm talking about is a case study we've been working on in Kenya. To the right, you see the small inset of the Kenyan countryside. We have been working in the far west in the Mau forest system. It's one of the head of the water towers in Kenya. The major land use types are also being seen on the right. On the top, it's the pointer here. So in the right top, you see the tropical forests, and the below part here depicts the tea plantations in the western part of Kenya. There's a lot of tea grown. Lipton tea is coming from that area. And then we have the smallholder agricultural systems. So basically these three land use types, and the interests of the different stakeholders in the different regions are completely manifold. So overall, it's a relatively wet area, up to 2,000 millimeters per year of rainfall, and the water is draining into Lake Victoria, also a hotspot of biodiversity in that region, and a lot of interest from politicians what happens to that country. In a former series, in a former talk by Björn Weser on March 22nd, he was reporting about the citizen science project itself, how it's set up. And here I'm talking about the data that came out and how we use them in the model. So in this figure here, you see the measured water level line here, the pale blue one, and the dots are the measurements by the citizens. And as you can see, they are following the radar data very nicely. Of course, there are some parts here where you have gaps, and the question was how good are these data to set up a hydrological model? We used a very simple one, like a ready-made or tailor-made thing from a catchment modeling framework that we are developing in our institute. It's a kind of toolbox where you can put together nicely bits and pieces to come up with a hydrological model. It turned out that the system is quite simple. So we have a storage box, like where the major water comes from. We have a surface water box that feeds into the storage box, and the surface water box, of course, is filled by precipitation. The outgoing losses are evapotranspiration to the atmosphere, and then both boxes of the surface water and the storages, they feed into the river. The objective functions we are using is the Spearman rank coefficient, because we are using the water level data to calibrate and validate the model. So we have not a water budget. We cannot close the water budget because the discharge data is missing. We're just using the changes of the water level to test the model itself. The additional thing that we're using to close or to better refine the overall volume is that we have a water balance filter that we developed from MODIS data, which is data on actual evapotranspiration, so that we have a second informative data set. Yeah, we then compared the relative performance of our models with the best one, so to say. We're using validation data from an automatic monitoring station to test our citizen science data, how good they are. We test the water balance filter, and overall, we come up with 6 independent calibration schemes, which I show you here. So first of all, we have the data sets, which are consisting of automatically measured discharge data. Remember, this is only for testing the whole approach. And these are the citizen data. So the citizen approach is to the right. We use the data set with the measured discharge and the measured water level in a common classical hydrological modeling way, testing it with Nash-Sutcliffe efficiency. We tested it then also in the same way as we test the citizen data. And to the right, we have the 2 calibration runs with the citizen data itself. So as you probably might guess already, that the common classical hydrological model application is very good. We have a Nash-Sutcliffe efficiency, which is very high, and it's almost optimal what we can get from the data that we are using. In the next step, we were testing how this optimum data set would behave if we only use this rank Spearman correlation to test it. And as you can also see, the relative performance dropped significantly down to only 66%. But if we switch on the filter, this water balance filter, we can increase it again to 85%, which is using citizen science data. If we came up with such a result, it would be very good for us. So in the next step, we were using our citizen data in a similar approach. And as you can see, the relative performance is as bad as it is if we use the automatically obtained data. And if we apply the filter again, it increases to 84% of the optimum, similar to what we can achieve by using measured discharge data. So the overall conclusion from this testing of the calibration schemes is that using citizen science data, we can come up to results which are almost as good as if we're using the automatically measured data from the station. How does such a graph look like? Here to the left, you can see the time series we were testing here for the calibration period to the left, and for the validation period here to the right. In this graph, I only show the citizen science data here, CS, with the Spearman rank correlation and the Spearman rank correlation with the filter, and the optimum again as a comparison, the NSE, so the efficiency of the approach by using the measured data from the station. And the darkest shadow here is the uncertainty around the predictions using the measured data from the station, and only slightly worse is this red, slightly paler area that is around the measured mean by using the Spearman rank coefficients and the filter together. So overall, our conclusions is that yes, the citizen science data have a significant value in using them for model applications. In our case, we also concluded that the objective function has a larger influence compared to the type of data. So it doesn't matter so much in our case whether we use the station data or the citizen science data, we always come to a good result. It's more important to come up with a good objective function. In this case, as I said, we tested this rank Spearman correlation and it was quite successful for us. The filter, that is something that we also found is using additional soft data, in our case, remote sensing data from evapotranspiration, is a very important aspect to improve the prediction capability of the model. As I said and showed, we increased it by almost 20% by adding the filter results. And using this filter or some other filter from remote sensing, there is a good and I think promising approach by combining the citizen science data amended by additional data from other sources to come up with reliable and good projections that people can use in their decision making. We also checked the quality of the different boxes, how the reduction in the uncertainty reduces by including this additional information. As you can see, the spread of the projections here to the left is quite large. As soon as we switch on the filters, the uncertainty is significantly reduced. And this is not only for the evapotranspiration, this is also for working for the storage box of the river of the major storage box, but also on the surface water box. So this again shows that the filter has a big effect and is needed.
2 minutes.
My conclusion is that the crowdsourced water level data can be used to calibrate the conceptual rainfall runoff model, at least in this system where we have been working. The question is whether it's working also in more complex areas, in more complex catchments. This is something that we're going to test in the future. The water level does not contain information on volume. That's why we were considering this additional water balance filter to improve the information content in that respect. The crowdsourced data in combination with the hydrologic modeling allows us to derive information on water resources that is important for people living in the area. And if you're interested in the model experiment and the parts of the validation and calibration aspects, have a look at the publication that is related to this work. Finally, I want to talk and give some ideas about the pros and cons of the this kind of data that we are collecting here. So in Kenya, in our catchment, it's very cost efficient. We use, it doesn't take a lot of administrative effort to run the project. The good thing is the people are very interested in, they have the feeling, and also they have the allowance to use the data. The public knowledge and awareness is quite improved. It's very nice working there with the people. They're happy having us there. The question is about the continuity. If we go what happens to the project and the data collection. The responsibility then is questionable. So that's a big issue after citizen science projects are stopping. A big difficulty in that area is that the public institutions are bypassed. They don't feel responsible anymore, and that just let us go. And the final question we have to the politicians is what happens to such ideas of data collection, because we have the feeling that politicians shirk the responsibility. And with that, I'd like to thank you all, the team, to do this work, and I'm happy for questions.
Okay, thanks a lot. Very interesting work and presentation, Lutz. As we'll save the questions for later and directly go on to the next presentation, and then take the time for questions afterwards. So now with the second talk that will be given by Hunter Smith. Hunter is at Living Lakes, Canada, and is a program coordinator there. And he has also studied background in water-related, but more in water security from the University of Saskatchewan. And he will talk about community-based water science and stewardship in the Canadian Columbia Basin. With that, I hand it over to you, Hunter.
Awesome. Thank you, Jan. You guys can see that, eh? Perfect. Good morning. As Jan said, I'm Hunter Smith, the coordinator for the Columbia Basin Water Monitoring Framework with Living Lakes, Canada. And today I'll be presenting on our Water Monitoring Framework program in the Columbia Basin Water Hub database and their role in integrating citizen-informed science into policy. I'll start with a brief overview of Living Lakes, Canada and the Canadian Columbia Basin where we're based. And I'll explain some background on the water monitoring framework, the water hub, and how our data can be used for modeling and policy change. So Living Lakes Canada is an award-winning NGO that facilitates collaboration in monitoring, restoration, and policy development initiatives for the long-term protection of Canada's lakes, rivers, wetlands, and watersheds. We have been leading water stewardship initiatives for over 20 years and facilitate science-based projects with a wide range of subjects, including groundwater, lake, stream, and wetland monitoring, foreshore health assessments, and biomonitoring for freshwater restoration. Our programs take place across Canada, but our focus is on the Canadian Columbia Basin. The upper Columbia River Basin includes the traditional territories of the Ktunaxa, the Glidley-Tene, the Secwepemc, the Sinixt, and the Silks First Nations, and is located in the southeast portion of the province of British Columbia in Western Canada. The Columbia River weaves across this landscape, flowing north from its headwaters in Canada before turning sharply south and flowing through Oregon and Washington states before emptying into the Pacific Ocean. The river is an important source of drinking water, hydroelectric power, and also serves as habitat for a variety of species. Intensifying climate impacts are influencing these water uses and the region's overall hydrological cycle. Historically, glaciers and snowmelt have provided a stable and reliable source of fresh water to communities and ecosystems year-round. Recent studies show that the rate glaciers are disappearing in the Canadian Columbia Basin is accelerating, and they suggest that the glacier melt contributions to stream flow have already passed peak flow. Compounding this, a low to no snow future in 30 to 60 years is predicted if greenhouse gas emissions can continue unabated. Climate impacts taking place now are presenting as extreme temperatures, wildfires, precipitation, and flooding, and are impacting water quality and quantity, as well as the timing of stream flow. This is the context for the water-related work that Living Lakes Canada is facilitating in this region. The Living Lakes Canada program I'm most heavily involved with is the Columbia Basin Water Monitoring Framework. This is an innovative monitoring network with the foundational goal of creating a water balance for the Columbia Basin and its watersheds. In order to plan for future land use and ensure sustainable water management, decision makers need to understand how much water is currently available across their watersheds and how climate change will continue to impact the water cycle. Following a recommended scientific water balance model has necessitated a broad approach to monitoring and provided insight into which climate and hydrometric parameters that we prioritize. The framework is designed to fill important data gaps in the water balance equation, as well as track climate impacts on water supply across the Canadian Columbia Basin. To help accomplish this in an area of over 100,000 square kilometers, the basin is divided into 10 hydrologic regions indicated by elevation bands and surface water runoff, reflecting broad variations in climate. This allows us to work in a stepwise fashion, rolling out the framework methodology in a few regions at a time. So last year in 2022, we successfully piloted the framework in 3 of these regions, shown here in purple. And this year we're expanding into 2 new regions shown in blue. In all 5 of these regions, we identified under-monitored areas through a comprehensive data gap analysis, and then led a collaborative community-focused approach to selecting the monitoring sites. This was done by forming local reference groups in each area of interest and holding public meetings and engaging in one-on-one conversation with a wide diversity of community members to ensure that the selected sites addressed local community water-related priorities and concerns. We collected data from our local reference groups using a variety of methods. This year, we were lucky enough to be able to host 6 in-person local reference group meetings across the 2 new areas of interest, as well as 2 online meetings. From these meetings, we've heard from 150 community members representing regional and provincial governments, local stewardship and water user groups, academia, private sector, industry, and Indigenous communities. And we heard from them through mapping activities and coordinator-led discussions. In addition to the larger meetings, we've had direct consultation with First Nations and local governments in each region to ensure that their concerns and priorities were at the forefront of the program's activities. To reach those who couldn't attend a meeting, we also developed an online survey that has seen over 100 respondents so far. This comprehensive community engagement has resulted in the identification of priority water bodies and environmental stressors and impacts that are unique to each local area. These impacts range from the impact of forestry and wildfires, the health of fish populations, the status of groundwater resources, the drying of wetlands, the impact of agriculture, and the future of drinking water availability and quality. These community-informed concerns, along with logistical information and the results of our data gap analysis, are then tabulated into a tool we call the Priority Monitoring Matrix, which was designed to help us select key monitoring sites that balance both scientific and social needs. In our pilot year, we used the PMM, the Priority Monitoring Matrix, to help us select sites for many of our existing stations. And we currently operate 31 hydrometric stations, 6 climate stations, 5 mid-elevation lake level stations, 6 high elevation lake monitoring sites, as well as 11 groundwater observation wells across our 3 pilot areas. This marks a huge increase over the 19 government-operated hydrometric stations that were one of the only sources of hydrometric data in these areas prior to our work. This map here shows the monitoring sites that Living Lakes Canada is overseeing across all of our monitoring programs in the Canadian Columbia Basin. Ancillary programs like our groundwater program and high elevation program contribute to the broader objectives of the Columbia Basin Water Monitoring Framework. And we work closely together with these programs to ensure that our efforts are aligned and efficient. For 2023, this year, and the second year of the framework project, we expect to install at least 20 more hydrometric stations, 8 lake level stations, and 4 climate stations by the end of the field season. Due to the technical and remote nature of hydrometric and climate monitoring, citizen science in its purest definition is not always possible. However, Living Lakes Canada supplements its community-informed approach through workshops and volunteer opportunities. Last year, we hosted 3 hydrometric monitoring workshops with the province. We plan to host 3 more of these workshops this spring, 1 in each new area of interest, and a 3rd in collaboration with Shuswap Band's New Guardian program. This year, we've placed importance on selecting a few monitoring sites that are more accessible, and these will serve as showcase sites and allow community members to see what we're doing and learn firsthand. Through our framework program, volunteers also participate as site stewards, and they check on our monitoring sites periodically and ensure everything's running as it should, download data off of our data loggers, and read our stat pages. In order to securely house all of this data, collected by our programs as well as community groups in the region, Living Lakes Canada developed the online Columbia Basin Water Hub database. The Water Hub is a central location for all water-related data, both current and historical in the region. This platform was launched in 2021 and now hosts over 300 data sets from 47 different organizations. And these numbers continue to grow as we connect and collaborate with new contributors. Prior to the development of the Water Hub, water data from the Columbia Valley region was often held on private computers or even on paper, and so there was a huge risk of this being lost. Now that data is available publicly for research and decision making. As an NGO, Living Lakes Canada is flexible, and this allows us to work with each contributor to support their data management practices and ensure that their data is stored and shared appropriately. Our individualized approach has increased the data quality, or quality of data management, practices of many of the groups that we work with. The Water Hub was designed to support data governance and to allow groups to maintain a level of control over how their data is shared, accessed, and used. This allows us to align with the First Nations principles of ownership, control, access, and possession, or OCAP, when we're working with First Nations data, and to support the unique needs and preferences of a wide range of contributors. Through working directly with each group on data management, upload, and sharing, we've created a strong relationship with the groups conducting water monitoring projects in the basin, which has further informed the development of the Columbia Basin Water Monitoring Framework project. Despite our growing number of data sets, the water monitoring framework is still in its infancy with only a year of data. However, one of our closely associated programs, Kootenay Watershed Science, has over 10 years of data collected from 7 hydrometric stations, 3 climate stations, and 2 lake level stations. KWS serves as a great example of how the framework will be able to support modeling efforts in the Columbia Basin. With a decade-long time series, we can start to calibrate a simulated watershed against our observation and work toward a predictive model of the Columbia Basin water balance. Using a modular hydrological model, we'd be able to see how different aspects of the hydrologic cycle respond to predicted changes in climate. That information can then be used by decision makers when planning water use allocations and environmental flows. As we continue to collect data, calibrations will become more fine-tuned and predictive models will become more accurate. In the context of the greater framework project, we hope to carry out similar modeling across all 10 of our hydrological regions, eventually producing a water balance model for the entire Canadian Columbia Basin. In the more immediate future, data collected through the Columbia Basin Water Monitoring Framework and our associated Living Lakes Canada programs will be used in policy development. Many of the communities within the Columbia Basin are currently developing climate adaptation strategies that require a strong understanding of their water resources now and into the future. When prompted to provide the most significant climate hazards in their jurisdiction, participants representing the Regional District of East Kootenay listed overland flooding, rain, and other storm events, as well as water storage or water shortage among their top concerns. Similarly, the Regional District of Central Kootenay listed water supply and floods as areas in which they could improve their climate resilience. Both of these regional governments plan to have a climate action plan in place within the next 2 to 3 years. And working with Living Lakes Canada's monitoring initiative is listed as a key next step in the RDCK's list of climate actions. Additionally, data collected through community engagement can help shape regional climate action plans by focusing them on local water interests and concerns. As we continue the As we continue the framework program, our watershed scale monitoring can help inform adaptive management strategies, allowing local governments to make sub-regional water conservation decisions. Our localized data focused on community concerns has endless applications for policy development, and the ease of access granted by the Columbia Basin Water Hub will ensure its uptake. Through the Columbia Basin Water Monitoring Framework and the Columbia Basin Water Hub, Living Lakes Canada is uniquely positioned to integrate community-informed monitoring practices into both predictive water modeling and policy development. We have an intimate knowledge of water priorities and concerns of a diverse set of rights holders and stakeholders, And we've made our data easily accessible for use through the Water Hub. With the preliminary data from the pilot year of the framework project becoming publicly available in the summer of 2023, we hope to further the Canadian Columbia Basin region's collective goal of identifying and initiating climate change adaptation strategies and watershed security for human communities and the ecosystems we rely on. So thank you for listening. My contact information is up on the screen if you have any questions that you want to send to me privately. You can also scan the QR code on the screen to get to the Living Lakes Canada site and follow us on social media. Thank you.
Well, thanks a lot, Hunter. That was very interesting to see this study here in the Columbia River. I encourage everyone to ask questions. Before we go into the questions, we'll give the two pop-up talk presenters a chance to present their short presentations, the two-minute presentations. In the meantime, please always think about questions, put them in the Q&A. And in the Q&A, you can also vote up questions if someone posts a question that you are interested in, because we might be a bit tight on time. It's important to know which questions are most important. And that, quickly, let me share the screen again. So we have two pop-up presenters or lightning talks. The first is by Kris from Cornell in the Hudson River Estuary Program. And I'll also ready to, to not switch screens too often, introduce the second one, which will be given by Kris Jennings. Kris is a hydrologist at Lincoln Intel in Boulder, Colorado. So with that, I give the word first to Kris and then to Kris.
Okay, hello everybody. And let me just show you what I've got here. So we are going to be talking today about one of my favorite fish, that is the American eel, Anguilla rostrata. Here are some live baby eels. These are called glass eels. These animals were hatched in the Atlantic Ocean about a year ago and spent a year traveling on currents to the east coast of North America, anywhere from Mexico to the Canadian Maritime provinces. From Florida to Maine, there is a really important interstate policy called the Atlantic States Marine Fisheries Commission that sets up protocols for sampling. Starting in 2008, we adapted those interstate protocols to expand glass eel monitoring so that high school students, watershed groups, family members could all get in, not just on the fun, but also on the science. You'll see here different students that are checking a funnel-shaped net, taking the eels out of that net every single day for 2 months in the spring, counting the eels, collecting some environmental data, and then very deliberately moving those eels upstream past barriers to connectivity like dams and poorly sized culverts. So what we have seen in doing this project now for 15 or 16 years, we've seen a bumpy but general increase in the ingress of American eels. So we're starting to see a hint that maybe eels, which are technically a depleted species, maybe there is something going on that eel numbers, at least as they come into the Hudson, are coming up a little bit. But you might be asking yourself, what does this have to do with hydrology? So what this has to do with hydrology is that eels are really, here in New York and throughout a lot of the East Coast, they're sort of the poster child, the mascot of stream connectivity. So any kind of topics that have to do with reconnecting streams, with right-sizing culverts, with dam mitigation, and even when appropriate, dam removal, the American eel really is the creature that is going to benefit tremendously from that. So as we build up this data set, we're also building up a community of people who care about an animal that is otherwise pretty much misaligned and ignored, even though they are absolutely springtime's cutest little critter. So if you'd like to find out more, please do a Google search for, or an internet search for Hudson River Eel Project. My email is on the screen there. I'd be happy to answer any more questions when the time comes up. 2 minutes, boom.
Thanks a lot, Kris. I have to say I have seen a lot of live cats recently on Zoom, but I've never seen a live fish. So that's the first one. That's great. Wonderful. Okay, with that, over to you, Keith.
Everyone, you all see my screen now?
Yeah.
All right. I unfortunately don't have any live animals, but well, I guess except for myself, I'm Keith Jennings. I'm with Mountain Rainer Snow, and we are funded by NASA, the Citizen Science for Earth Systems program. The origin of this project is what is on the face, a pretty seemingly easy problem, and that's partitioning incoming precipitation into rain and snow. The reason we have to do this is there's not many observations of rain versus snow, so oftentimes we have to use meteorological data, like is illustrated in that picture on the left-hand side, where there's a MET station. So we use MET data and hydrologic models, land surface models, to partition precipitation into rain and snow, and we can also use satellite and satellite products. But the problem is, even though the freezing point of water is an unequivocal 32 degrees Fahrenheit or 0 degrees Celsius, oftentimes we get precipitation in its solid form as snow at air temperatures slightly to well above freezing, depending on where you are in the country. So we're getting at this using community observers, and we engage with our community by using two-way text messaging to let them know of incoming storms. We have a simple, straightforward web app where people can mark whether it's raining or snowing or mixed precipitation at their particular location and point in time. And we also have options to connect and learn more. And we do that through Ask Me Anything sessions, through digital report backs to the community, and also live in-person presentations. And what we've found through the past few years of this project is that there are fundamental hydrologic model limitations. So as I noted, we often use model methods to partition precipitation into rain and snow. And I don't want you to try to hurt your eyes looking at all the labels on the y-axis on the plot on the left. But what I want to draw your attention to is the method success rate. So wherever you see yellow, that's good. We're accurately predicting rain or snow. Wherever you see the darker colors, the purples, the dark blues, that's where we're doing a bad job. So no matter what method you're using, an air temperature threshold, a wet bulb temperature threshold, statistical model, machine learning method, they all degrade at air temperature slightly above freezing to about 10 degrees Celsius. And what we found on the right-hand side in that little subplot is that when we look at all the observations from our community observers, there's a strong overlap slightly above 0 degrees Celsius in rain, snow, and mixed precipitation. So if you're only using near surface meteorology in your models, you're never going to be able to accurately tease apart those things because their conditions are almost indistinguishable from one another. So in the coming years of this project, we're working with our partners how to better integrate these observations into land surface models, hydrologic models, and remote sensing products. And you can contact me at the email there or visit our website at rainersnow.org, and then all of our partner institutions are on the bottom. Thanks.
Wonderful, very interesting work. So with that, we are now going over to questions and discussions. We have one question in the Q&A here. How is the data collected? And I think that was related to your talk, Hunter.
Yeah, so our data is collected with a variety of sensors depending on what the station is. So we've got pressure sensors as well as stage measurements, and we do flow tracking for our hydrometric stations. And we have barometric pressure, radiation, wind speed and direction, precipitation at our climate stations. And the data from those stations is downloaded periodically. So for some stations, like it's a kind of like a 5 times per year. We're also currently working on integrating telemetry, so that'll allow us to push the data to our database on an hourly basis, and then people will be able to see our climate data in near real time.
And Derek just specified that actually the question was for Lutz after all, but he wanted to hear from both, so and I think we all are interested in that. So Lutz, can you also say something about your data collection? You're still muted. Yeah.
The data collection is based on reading gauge level readings. So we have placed gauges in the stream, and there's a small sign that's describing how to read the gauge, the staff gauge, which is, well, straightforward and simple. The data then is transferred by SMS to a local server, which we set up in Kenya. The reason is we didn't want to use smartphones, because at the time when we started, smartphones in the countryside were just not common, but lots of people have a simple mobile phone, so recording by SMS is a way to go. And we checked different ways of really citizen-based without any payment. Then we also had a gauging station where we reimbursed people, but the participation rate was better, but not so much better. So we, in most of the cases, we stick to volunteer data recording and sending the data. And it was really quite surprising how many people participated. Some of them, of course, only 1, 2, 3 times, but we have people who are regularly sending data voluntarily. We didn't train them at all. So the readings are so simple that there's no training needed. And that's, I think, one benefit if you want to have the public involved. We didn't want to train people because it was also almost impossible for us to do that, of course. Yeah.
Thanks. There was another question which was put into the chat. I think that was for you, Lutz, also about groundwater. So from your talk, it seemed that it was not significant, but can you specify on the importance of groundwater and how that is reflected in your model? Yeah.
So in our system, the groundwater is not really relevant. So the simulations we are running can get like Nash-Sutcliffe efficiencies of 0.9, 0.95 without a lower storage box in the model. So the groundwater obviously is not so important in the stream runoff in this system. The reason is likely because the rainfall rates are so high that and it's very flashy hydrograph. As soon as it starts raining, the water is directly in the stream. Of course, it could be going through the groundwater, but the time delay is not so important that it really affects our system there, which is very good for us because then the citizen science data is very useful. We don't have any groundwater data from citizens, and we were thinking of using groundwater or wells dug by local people, but it was, at least at this stage, difficult to get data, reliable data from that areas. So it was good luck also with our system, I would say.
Well, you have to choose your systems. We have a question for Kris here, jumping a bit. In the graph here, in the time series you showed, there were some dips in the, besides the kind of general increasing, but there were some dips, 2014, 15, and then also 2021, where it was much lower, so the counts. So is there any explanation, or so can we expect it, or do you already know the numbers for 22, 23?
I do. So there's a couple parts to that answer. That the 2014 and 2015 dips, to me, kind of still float in that kind of let's say accepted range of variability. And as everybody with fish science in particular, you're going to have some pretty high degrees of variability in your data. The 2021 is a big dip, particularly because of the big shocker, which was 2020 was such an astronomically high year of eels. And I really don't want to, I can't find a good mechanism to attribute that to COVID, but of course, that is the question I get all the time. That big dip in 2021, I don't know, because we did see numbers come back up in 2022, and I would say that 2023 are also in that. But I think that with eels, and I believe that every eel researcher probably in the world would agree, there's a pretty high range of variability when just looking at season to season. You really have to step back, way back, to see a big index there. But those are great questions. Not all of them have clear answers.
Okay, well, it's always very good. Thanks. Lutz, you in your talk you want you want or you said, well, it's a problem if the kind of official ways agencies are bypassed by the citizen science project. It could be risky, and with that respect, one could wonder, well, is in Canada, Hunter, how is your relationship to Environment Canada, and do they feel bypassed, or how do we include those official kind of ways?
Yeah, so we work pretty closely with all levels of government. We work with regional governments, provincial government, and the federal government. Right now, the provincial government just announced funds for water monitoring, and the federal government is kind of working on the Canada Water Agency. So there's a lot of collaboration between us and government.
Okay. Yeah, Lutz, do you want to add?
Yeah, I think so. My comment was particularly made to the situation where we are working in, and maybe that is scalable to other countries in the global south. The issue in Kenya is that the local water services, they don't have money for anything. They have a car, but they don't have petrol to run it. They have an instrument, but they don't have batteries to put them in the machine, so they don't work. And what they do is they follow us when we go to the stream, and they want to get paid supporting us, even though they don't support us. But the problem is they don't have any resources to work with. And now there come these rich people from the west or the north or whatever, and do volunteer measurements with local people, and it works. They have the feeling all of a sudden or immediately that they are not needed anymore. And that's I think that's really a big issue. At least in our area, it is a big problem. We don't want to do their work, of course not. But I mean, what you could tell the politicians is, well, tell your local extension services or your local administration people that they should work together with the people do, and support them. And you have to pay them for organizing that. You don't have to pay batteries and petrol.
Good. Certainly a lot of this cultural-ish challenges also in special situations. Related to that, a question to you, Hunter. You mentioned the kind of your linkages to the First Nation people. I, now being the moment here on sabbatical in San Diego, I also seen a little bit of that. And I'm wondering that what do you see as the biggest challenge to bring this indigenous knowledge together with the, well, how should I say, Western science way, that the tradition that we have of measuring time series things, where we, yeah, it's a kind of very different approach to the approach that has been around for generations for the First Nations. So what do you see as the biggest challenge that bring these two together?
Yeah, I can't speak for the First Nations, obviously. I think one of the biggest issues is capacity. I think a lot of the time there's like a Western time frame put onto projects that it just doesn't work with First Nations communities. And so, yeah, taking the time to build a relationship with communities is definitely the first step.
Also from the chat here, a question to Kris. This distinction between rain and snow seems very obvious, but there is some kind of, probably also in the observation, some kind of gray zone where if it's raining, snowing, or people might judge it differently and say, well, this is snow or this is rain, especially if you involve a lot of different people and maybe not trained. How difficult would you say is it to make the distinction, and how different would different people judge whether an event is a rain event or a snow event?
Yeah, that's a really good question. I've found different people in life are either lumpers or splitters when it comes to classifying things. I'm very much a lumper. So our focus for this project is rain and snow, but we also include a mixed precipitation type, sort of as that catch-all when you do have precipitation that's falling in both a liquid and solid form. And we've had really good reports and questions from our community observers about that. And one of the things we found a good rule to go by is that if you can't really tell what the phase is, if it's raining or snowing, if it looks like wet snow, or maybe there's some solid particles mixed in, that it's probably mixed. I also use the jacket test. So if you're outside and you can see liquid falling on your jacket, but also snowflakes coming in, then it's probably mixed precipitation as well. But you could go even more granular than that. And we just wanted to stick with the three main categories instead of worrying about the differences between graupel and pellets and sleet, so on and so forth.
Yeah, interesting. Thanks. Then we have another question in the Q&A about the data collection during high flow events, which are of course oftentimes the most interesting, but it's also might be most challenging to get people out. There might be safety concerns, but also just that people might be less likely to be out if it's high flow and raining. I guess this question to both Lutz and maybe extreme snowfall might also be so. The others might also join in there. How to ensure to get the extreme values and get observation during those, which are might be most informative. Anyone wants to start there?
Maybe I start. I think you cannot really guide that, and it's unlikely that you really get the high flows. It's also unlikely in Germany that you get the high flows, because also hydrologists avoid pouring weather conditions sometimes, I guess. So our philosophy in the whole approach is that we don't want to train the people a lot. We were really looking at laymen and bypassers. We're not informing anyone or training anyone. We just put out the signpost, and we still have, I would say, at 90% of the flow conditions, we get at least some point of data. And if it's too high, if you can't see the gauging staffing gauge anymore, then, well, it's not helpful anyway, or not possible to measure.
For our program, our data isn't used for early warning of floods. We don't have real-time data for our hydrometric data yet. The high flow events. So our program, kind of to jump back to that question about government involvement, the government in Canada kind of typically does measurements on like the larger systems, and we've kind of taken a look at the smaller side of streams in the area because they're under monitored, and so we've got kind of like a limit on how much like how big of a stream that we monitor. So high flow isn't as big of an issue for us.
Good. Thinking of more questions. Doesn't seem. All that. Okay. Well, seems that we addressed a lot of the questions that came up. We're reaching the top of the hour, and by this also the end of this seminar series. The seminar today, which also is the end of the seminar series in total. A big thanks to all of the presenters today. It was really interesting. Learned a lot of new things. I saw fish for the first time on Zoom. That was great. Thanks also to the co-organizers, Ilja, Kris, and Thom. Was a nice series that we were able to put together. A big thanks to Julia and CUAHSI for organizing that. Without that kind of lot of logistic background work, helping to organize things, that wouldn't have been possible. So Julia did a wonderful job and supported us in any way that was thought we could think of, even beyond what we could think of. So that was really, really much appreciated that we could pull this series off. The series, all of the 8 seminars are all recorded. They're available, or will be. The last one will be available on YouTube. So you can, if you missed something, you can watch it there. And given the interest, we might consider doing something similar at some point. Again, otherwise, I hope to see a lot of you on coming conferences somewhere, anywhere. I think we have so much common interest and so much common issues that we are challenges that we are struggling with in citizen science projects. So I think interaction is certainly a very useful thing. With that, I wish you a nice day if you're in the US, a nice evening if you're in Europe, and good night if you're in Asia. And yeah, see you somewhere soon again.
Thank you.